Okay, I have no idea. Oh, let's switch this to demos. Okay, there we go. We're on demos. So we've got 5. The same light bulbs are all the same. I think they're 25-watt light bulbs, all incandescent, even though this one looks a little taller. Right now, with all these switches open, they are in series. When I plug them in, I will step around to do this. Where is my plug? Here it is. Plug. Ta-da! They've all turned on, and they are not that bright.
Is there a reason that one's so tall?
I couldn't find any more of these. In the same wattage, So notice they're all the same brightness, at least. The other ones that I had in the actual bulb were different wattages and therefore different resistors and different brightnesses. So all these resistances are the same. Now I'm going to start doing weird stuff. I'm going to start closing these 4 switches and watch what happens. Ba. 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 Bum, 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 bum. Yeah, wait, what? I'm going to do this in reverse now. Ready? Ba. 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 Chicken noise. Here's what I'd like you to try to do. When all of these switches are open, all the light bulbs are on, and they are in series, I'd like you to put 4 switches into that circuit so that when I close them, the various effects that you have seen here occur. I want you to try that too at home. I'm going to pause this video, see what you come up with, and then we'll talk about it. Okay, so let's take a look at this. If you're drawing these in series, you might want to draw them like this, where, oh, these are light bulbs, let's draw them as such. 1, 2, 3, 4, 5. You can't see what I'm doing, can you?
No.
Well, the people online can, class, so they're the ones who matters. When that turns on, you'll be able to see. Okay, so what I have is just on the board already. So here are 5 light bulbs, right? I'm going to do something weird. I'm going to draw this in a slightly different way. I'm going to say, here's our 120 volts coming from the wall. And I'm going to draw it like this. I'm going to draw it like that. Now what I can do is I'm just going to connect these gap regions with switches.
Yep.
Why? Well, let's take a look at this. If I close this first switch here, current is going to come out of my wall, and it's going to run through this gap. It's going to dodge the first 2 light bulbs, right? Because, here, let me move this light bulb a little bit easier to see. It's going to dodge the first 2 light bulbs, and then because the rest of these last 2 switches are open, the current has to come down, across, and give me 3, which, when I close it, boom, that's what I see, okay? Now, if I close the next one, here, well, now my circuit, the current can come down, and then, well, I could come down and try to travel across the light bulb. That's a lot of work. I don't want to do that. So my current's going to come down. Well, can I do this? It's going to come. Oops, I did this on the wrong side. I did this on the wrong side. This one's still open. Apologies. Which one did I close? No, I should have closed this one, yeah. When this one gets closed here, current comes down. Did I draw this right? Did I already mess this up? Oh no, yeah, this makes sense. Wait, no, it doesn't. Why doesn't this make sense? What am I doing wrong here? Tom, talk to me.
Did you put all the switches on the same side?
No, here. What did I... I'm going to redraw this. For some reason, I'm having a huge brain fart at the moment. Bulb, 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 bulb. And then we go home. For the first one, when I connect it here, I bypass these two. And then...
Wait, would it go diagonal then?
no.
Because it has to skip the filters too.
I need to skip the next one.
Yeah, so you take it from that corner and draw it.
Draw like
a
a
linear line,
skip
like-
them all technically.
The linear line.
Yeah, that would work because then you.
Skip that ball.
Yeah.
Oh, yeah. It's easier when I do this. Don't want to go, so I go through. Oh, okay, yep.
Yeah, because if you were to take the first switch and turn it that one off.
So you can't see this very easily, but when I close this, these three here have not gone out. They're actually dimly lit. Okay, and if you want to zoom in on that, you can't, but if you want to come up here later, they're actually dimly lit here. Okay, because what's happening is when I close this second one, when I didn't have anything there, the current had to come through, it came down, and then it went through. So I only had these three bulbs, the middle, and then these two in existence. When I close this back switch, what actually occurs here is I can now take my current, I can now take my current, and when I send it through here, because that's how it has to go, it can begin to backtrack up and dimly light these. Okay? It's not going to do it a lot, because this current has to split up here, and it has to fully come down through here. So that's why these are dim, or these three are dim, and these ones are full in that regard. If I close the next one, what we see right here is just the last bulb go, because now I'm just giving this a straight path out. And when I close this bulb, or this switch, all of these are going to light right here, because now, when I look at this, I'm at 120 volts on this side, I'm at 0 volts all on this side here, and that means I have the same voltage drop going across all of these light bulbs. Because we equate the idea of power equaling a current multiplied by a voltage, I just really slammed up my voltage here. What I actually also did is I increased the total current through this. When these are all in parallel like they are now, there's less total resistance in the system, and since the same voltage drop occurs, that means a lot more current exists. I can also think about this as being V squared over R here. The light bulbs are all the same resistance, but over each light bulb, more of a current drop had to occur here. Each light bulb's taking 120 now, where before, if the 120 was spread across 5 of them, each one's only taking a piece of that, right? So that's why in this case, when they're all in parallel, we have this super bright structure. Here, just this one is actually lit, nothing kicks back. And here, these ones actually, the filament in there is dimly turned on, and these ones are much brighter, okay? And by doing like weird combinations, you can get all sorts of weird stuff like this, where we have to come up here. We can't go down here, so we cross this bulb. We can go here. These three in the middle are not off. They're dimly lit, because I can go over and over and over if I want, or I can go over and just down and out. So yeah, we get all sorts of weird little things. And like this one here, I come up and I pass over this, and then I go out. So I don't even need to hit any of the other bulbs, because since this switch is open, no current can come down through here, and that means that this switch here isn't doing anything in this setup. So it's a kind of a weird little circuit there. It's definitely weird to look at. We were having some problems looking at it at the computer. But it's a neat little thing to think about in terms of power. Because when we are thinking about power, power equates to this brightness idea. Okay, a joules per second, which is a watt when we think about it. And that's why normally when you buy light bulbs, you buy them by their wattage. Nowadays, though, with incandescence being phased out and LEDs coming in, you tend to look at lumens instead for the actual luminosity of it. But for a long time, the idea of a wattage or power was thought of as your brightness. So if you're asked about problems with light bulbs and how bright they are, really think about how much power they are outputting to do that. Okay? And that's that little demo. I guess the next question is, how do multiple switches turn off the same bulb? But that's for a later date.